share my screen. Okay. So the first thing I want to talk about is, you can think of it sort of as an adjunct to a lot of the things we're talking about, and that is, when you have a model, how are you going to measure whether it's good or bad? And so we want to measure how accurate it is. Okay. So the way we do this, and we've seen this a lot, is we have loss functions, right? So we do it by deciding what we mean by how good it is with our loss functions, and we create this loss function, L of y, f of xy, oops. Well, that yi is your actual value, f of x is your prediction, and it's a measure of how good we think our prediction is. So when we're trying to predict numbers, there's a pretty standard one. We use the MSE, mean square error, which is the square root of, we take each actual value and its prediction, we square the difference, we add them up, and then we take the square root. This is not the only possibility. Actually, last week we saw that the key to gradient boosting is a loss function that, at least at first blush, is not intuitive. There are actual reasons why it came about. It wasn't picked out of the blue, and it wasn't just pure luck that it worked. But you know, it was certainly something more complicated than the MSE. So, and of course, the speed of an XG boost and lightning boost is based on understanding how these loss functions look like. I just want to point out another very popular one is the absolute value. That is, we take the difference between our value and our prediction to be the absolute value of the difference. Now, the advantage of this is it's less dependent on outliers. And I think this is kind of a cute point, so I wanted to actually show this in what sense this is true. So suppose we have a data set, we have just n numbers, and we wish to find one number, which I'm going to call m, that is one statistic to summarize the data set. That is, if we want to, if we want to find a single number. Now, typically, we will look at the mean, but well, you decide what's best by looking at the loss function. So we have some unknown loss function, L, and we want to find the loss function. We want to find the m that minimizes the loss. Now, in this case, your prediction is just the xi, and we want to find the one that minimizes that. Now, if you use the regular square loss, then you want to find the value m, which minimizes the sum of xi minus m quantity squared, and that is the mean square error. And you can see pretty easily that in this case, you should take for m the mean of all the data points. And why is that? If you differentiate this expression with respect to m, then you set that equal to 0. That'll give you the m. When you solve for m, that'll give you the smallest value. But simply, this is 2 times minus 2, because there's a minus sign there, times the sum of the xi minus m. Well, when you solve that, this means the sum of the xi is just n times m. That is, m is the sum of the xi over n. So we should take for m the mean. So this is why the mean is nice. It's a good statistic, and it's the best single statistic you can use if you want to summarize your data set with one number. Of course, the one moral of this whole 10-week experience is that that's a terrible idea, but it should have best be a starting point. But what if you use, instead of the squares, you use the L1. So in other words, you want to find the m that best works when you're looking at the absolute value of the xi minus m. Now, when you differentiate this, what's going to happen? Well, we can certainly eliminate the cases where xi equals m, because that's just contributing 0 to the sum, so it doesn't matter. So you have two cases, either xi is bigger than m or xi is less than m, right? So now when you differentiate, you're just going to get a linear expression in m. And if m is bigger than, if m is smaller than an xi, we just get 1. And if did I do this right? If xi is bigger, no, I think I wrote it wrong. I think if xi is smaller than m, you get minus 1s. If xi is bigger than 1, if xi is bigger than m, you get just plus m. Okay, I wrote it right. But you just get this difference between the sum. You add 1 where xi is less than 1, and you subtract 1 where xi is greater than 1. So when is that sum minimized? It's minimized when m is balanced with respect to being in the middle of the xi, that is, m is the median. So you can see that when you choose the median, when you choose L1, you're going to get loss functions that are less susceptible to outlying values. I think that's a cute little fact, so I wish to explain it. Okay, so for binaries, for categorical outcomes, we've used accuracy and entropy, but we can say a lot more. And we're going to see this a lot tonight, so let me just remind you, we can have something is true and you predict it's true, that's a true positive. Something is true and you predict false, that's falsely predicting negative or a false negative. Vice versa, you can predict true and it's actually false, that's a false positive. And a true negative is it is false and you predict false. So we have those 4 things, and this is what we call the confusion matrix. And well, what I really want to say is that it's important to understand how important each of these 4 things are. For example, if you're trying to determine if someone has cancer, you're very concerned to get the true positives. True negatives are less important. You really want to have very few cases of false negative. So you want to do things so that you're going to maximize sort of true positive. And the other point I want to make is that whenever we produce these models which produce probabilities, then we don't really just get one thing. We get a family of predictions, because for any probability between 0 and 1, we can use the probability of the event being greater than p as being the criteria for declaring something yes. For example, in our data point like this, we can just say we're going to call something true if the probability of it being true is 0.7. In the cancer case, we may want to go and make it low. We might want to say instead of 50, we want 40 or 33% chance, because you just really want to make sure that, anyone who could have cancer, you're screening out. Okay? So, but just for a note, when we did the credit example, we used p equals 0.5. In other words, when we wanted to see what our predictions were, we created a probability, and we said, if the probability of default is 0.5 or greater, we're going to say they're in default. If the probability of default is less than half, we're going to say they've not defaulted. And that's what we did for our predictions. And that's pretty typical. You see this a lot. Your model actually produces probabilities, and then you just need to decide on some discrete criteria. And as I was saying, there are times when you may want to use a lower value, and this slide just points out the cancer example. All right. So it's a little thought experiment. If we use as a criteria the probability that you're going to get something to be true is greater than 2, would we have more false positives or less false positives? And remember, false positive means that we say something is true even though it isn't. So what do we think here? Is it 1 or 2?
Would have more false positive, less false positive.
So if we say the probability, if we're going to declare something to be true.
Oh no, sorry. I will say more false positive, because every time you will say it's a positive because it's very low bar.
Right. We set a very low bar for saying something's true. You're going to create a lot of false positives.
Right.
Right. So so yes. On the other hand, if you were very strict and said we demand that there's a 90% probability of something being true, in this case we'd have much less false positives.
Yeah.
There would be a lot more false negatives, though, because presumably when we're demanding a 90% probability, there's lots of cases that will be true, but we're going to declare them to be false, because we basically said only if we're absolutely morally certain something, or very close to morally certain that something is true, will we call it. So, in essence, when you produce a model with probabilities, you can, for every p, you get sort of like the false positive rate and the false negative rate based on this. So you can get pairs of false positive, true positive, and you can graph them for every probability. Now, ideally, even if you took probability equal to b 0.01, it would correctly identify every true example and correctly identify every false example. Most models aren't going to be even vaguely that good. but that would be the ideal thing. But you do get for every probability a pair, and what you're doing is, what you expect to see is, as you move along allowing more false negatives, you're going to have a higher, true positive rate. Excuse me, as you allow more false negatives, you're going to have a better true positive rate. So, and that curve is called the ROC curve. And so, as I say, as the false positive increases, so does true positives, because it makes sense that if you're just increasing the criteria, you're allowing more positives, you're going to have more true positives as well as more false positives. And if
Yep. If we have more false positives, then there will be less true positive, right?
No, because just say you say everything is positive.
Okay.
Then you can have a lot of false positives and a lot of true positives too.
No, but what do we mean by positive? Because positive, we are saying that false positive is that we are categorizing like everything.
What we mean by true positive is we've said it's positive and we've said it's true and it is true.
Right.
What we mean by false positive is we said it's true and it's not.
Right.
So if we set the criteria at probability 0, then we're going to say everything is positive. Our true positive rate is going to be 100. We're going to correctly classify everything that's positive. Right. We're also going to completely misqualify everything that's negative. We're going to have a high false positive rate too.
Okay.
So when p equals 0, we get everything. When p equals 1, we're essentially going to have no very low true positive rate. We're only going to call something to be positive if its probability is 100%, 100%, but we're going to have a very small false positive rate. We should have very few things that we're calling true that aren't.
Okay.
So this curve starts out as 0, 0, and winds up at 1, 1. And the best thing would be if it sort of made a beeline, if it went as close as possible to the point 0, 1 very early on. Because if you think about it, what this would mean is that it's getting almost nothing, it's calling almost nothing. 0, 1 is the point at which nothing you called true is false and everything you called true is true. It's perfect classification. And this is the ROC curve. So you can use an ROC curve, which gives you this sort of value for every probability. You can use it as a measure of how accurate a test is. So if you draw the diagonal line y equal x, that's the line where your number of false positives is the number of true positives. So in essence, that's a 50-50 guess. So if you will, more accurately, it's the line at which your accuracy is 50%. So if your ROC curve actually looks like the diagonal line, and I wish, for some reason, this refused to compile, I did have a diagram of it. But if you drew the 50-50 line, that would mean for every probability you chose, you were 50% accurate. Okay? It was like flipping a coin. Now, of course, you'd always want the ROC curve to be above it, and you'd want it overall to be above it. And the area between the ROC curve and the diagonal is called the AUC, or area under the curve, and it's a measure of how well the model performs. Because the more your curve is above, the ROC curve is above this 50-50 line, the better the model is doing. Now, that doesn't speak to the point of which P you should pick, but it does speak to the overall quality of the model. Now, I agree these things, well, to me, these things are confusing and they take a while to sink in. So A, I can tell you there'll be plenty more talk about this later today. And B, does anyone, Anish, Tejas, do you want to ask any questions about this? Is there something I could say to help clarify it? Do you want me? Why don't I just pause, for about 10 seconds, and you can see if the thing's in and see if you have any thoughts.
Well, it will be very interesting to see this ROC curve plotted. So that will give us like much better visual understanding of how it looks.
Yeah.
Compared to y equal to x9.
I'm going to skip way ahead because I have one drawn here. I think it's in here. Yeah, here. Oops. There.
Yeah.
Now here it's not plotted against 0, 0, unfortunately. I had trouble getting that right. But you can see this is the 50-50 line.
Yeah.
And you see here it is making a beeline. So once it got to this value, well, of course, it can't start there. It does pretty good. And you can see my data here was very discrete. But you can see you can see what points I've got new data points. You can see it getting better and better. And finally at this point, so this is pretty high.
Yeah.
It's somewhere about P equal 0.85 maybe, a little bit better than 0.8. You're as good as you can get, you're at 1. Okay?
Yeah.
So you can see the AUC is this area here above the line x equal 1. Okay, now I have to find, okay, so back to that. So to summarize again, the number of false positives and true positives is related, and the more false positives you have, the more true positives you're going to have, and you can graph this relationship, and it's called the ROC curve. And the difference between the ROC curve and your 50-50 guess, random guessing if you will, is called the AUC, the area under curve, and it's a measure of how much better your algorithm does than random guessing. Okay. So along with this, the other thing that we see a lot is what's called the confusion matrix, and I think I showed it to you before, but it's always useful to look at a confusion matrix because that'll show you sort of in down-to-town terms. I mean, and there may be times when, true negatives are more important than true positives, or true positives are more important than true negatives. But it can also help because it can show you where your algorithm is failing. I remember, Niels, do you remember a couple of years ago when you did the currency data and he had a test that looked like it was doing really well, but it turned out that once you looked at the confusion matrix, you could see it really wasn't doing well. It was just saying most of the time nothing was going on. And since nothing going on was, the 98% case, it was just really good at predicting this, which was the easy thing.
Right.
Now,
yeah, very unbalanced data set.
Very unbalanced data set. And so actually there is a measure that deals with that. And it's either the next topic or the topic after. Let me skip this, that's not important. And so here we are, and that's kappa. And kappa is a very intuitive statistic, but it doesn't fit in any theory. It's not like, mean and standard deviation, which, it's not a standard statistic. There's no statistical theory, but it is a very nice measure. And so this is one of my favorite stories, so you all get to hear it. And that is, and this is true, it's absolutely true. In the middle of 8th grade, I moved schools and they put me in French class. In the new school, they had been learning French for a year and a half. In my old school, I had been avoiding learning French for a year and a half. And since my teacher was superannuated, it had worked. And so I got a 0 on my first test. And the teacher said, bring it home, have your father sign it. My father looked and said, well, what's going on? I was a pretty good student. I said, well, they're a year and a half into the program, and I don't know any French. I'll learn it, but really, I don't know it. I was in this class 3 days, and what can I tell you? He said, okay. And he wrote up, I'm sure he'll improve. The next test, I got a 60. And again, the teacher was not impressed and told me to have my father sign it. And my father took a look at it and said, well, what's going on? And I said, well, if you think about it, Dad, I actually did pretty good. In the period between the two tests, 2 or 3 weeks, I've gone from knowing no French to almost being caught up. I mean, it's been a lot of work, but I'm getting there. And his comment was, I told you he would improve. And I guess the point of it is, and the point of his joke was that, there's always a best guess. And if you randomly guess, you'll be the best guess, you'll be correct more than time. So when I got a 0 for me to say I'm going to improve, that was a highly likely guess, and that was the humor. And so what kappa wants to measure is how much better than just random guessing is your guess or your estimate. Let me skip this slide in the interest of brevity. But I would the gist of what it's saying is if there's in most standard numerical measures, random guessing doesn't give you anything interesting. Okay, so random accuracy is the dumb prediction, which is if you have two classes, you always guess the majority class. So for example, in Neil's currency, I think it was something like 98% of the time, there was no move. So if you just guessed 98, no move all the time, you were 98% accurate. And as I write here, if you have a binary classification that's 75% yes, and you always guess yes, you're going to be 75% accurate. So random accuracy is just you guess is always going to be the guess the larger of whether it's always right or always wrong, true or positive. So the observed accuracy is the times you're right over all the times you're right. That is the percentage you get correct. So, I mean, there's a subtle thing. It depends on, I call it the class distribution. Observed accuracy is going to be a function of how much you can improve, how balanced the classes are. So, to explain what I mean, if a random guess is already 80% accurate, we can't improve by more than 20%. On the other hand, if it's a 50-50 thing then it's no problem to go to prove your prediction is 75-25. And on the one hand, you've improved your, accuracy by 25%. On the other hand, you're still less accurate than the random guess in the other case. So kappa is simply a way to measure that. So what does kappa is what the percentage you do get right minus the dumb guess, so how much you improve, divided by how much you could improve, right? So if random accuracy is 80%, the most you could improve is 20%. So observed accuracy minus random accuracy has to be between 0 and 20%. And so this tells you how much of what you could capture you have captured, right? So in the worst case, if you just take the random guess, kappa is 0. If you're perfect, if you get everything right, then you get an observed accuracy of 1, and your kappa becomes 1. So kappa is between 0 and 1. And it tells you how much you can improve. So it's a very useful thing. And you see it in a lot of places, including in Carat. Okay? So I wrote this for a while, and I don't really know, but what is good kappa? 0.75 is considered excellent, 0.4 to 0.75 good, and 0.4 poor. And that's according to Wikipedia. But, in the land of the blind, the one-eyed man is king, and he wins the races too, which is to say that, if you have a bunch of models and none of them have good kappa, still the one that has the best kappa is the best you're going to do. Okay? And as I said, kappa is used extensively in Carat. It's one of the measures it uses. All right, so I just wanted to go through one example because I think sometimes when you see these things, you can do it. So suppose you have a bunch of pictures of dogs and cats, and you have 70 of the pictures are of dogs and 30 of the pictures are cats. And here's your confusion matrix. You guess dog 68 times, you're right 62, you're wrong 6. You guess cat 32 times, you're wrong 8 times, you're right 24. So the majority classes, I say it's always dogs, so random accuracy is 70%. You can check very simply because I made the numbers nice that you're right 86 times, so you're right 86% of the time. So your kappa turns out to be 0.53. You've improved slightly over half, right? You have 0.3 is the maximum you could improve, and you've improved 0.16. So you've taken away something like 53% of the errors that you make if you guess randomly. Okay? And just to do one more example, another 100 things.
Professor, in the previous example, how did we get the random accuracy? I didn't follow that part. Sorry.
Well, random accuracy is to guess the dominant class. There are 70 dogs and 30 cats, right? So random accuracy is to always guess dog. If I guess dog, I'm right 70% of the time because 70 of the pictures are of dogs, right?
Okay. So in the previous slide, I think where the observed accuracy minus, I think, random accuracy. Why was it said that it would numerator would always be greater than, would always be positive? I mean, observed
Well,
accuracy can be
your
less than that.
accuracy, how accurate can you be? You can't be better than 100%.
Right.
You can't guess, it can't have more than one, right? One is, 100%.
No, agreed. I'm talking about the numerator, right?
Oh, why is the observed accuracy always greater than random accuracy?
Yeah.
Well, I mean, this is to my mind like the question Manish was asking. If your model doesn't do better than random accuracy, then you should take the opposite of your model for your model.
Right.
Right. If my model said 50-50, dogs and cats, I just would dismiss that model. I would, sort of like, if you will, being better than random accuracy is typically a minimum, a very low barrier for your model to use.
Right.
If you can't do better than a random guess, what good are you?
Right.
We're led to the famous example of Homer, which has to say, in the episode where he has to always say, yes, he doesn't want the power plant to blow up. They should hit the safety valve, and he eventually gets a bird to do it, hit the yes every time. Okay, so there's another example. It's 50-50, so it's a little more disingenuous. If I guess my random accuracy, my dumb model, if it doesn't do better than 50%, I'm kind of wasting my time. Now in this case, though, my observed accuracy is 30 plus 36 is 66. So I've improved my random guess is 16%, which is the same improvement as last time. But in this case, cap is 0.32 as opposed to 0.53. And why? And that's because it's easier to improve over a 50-50 guess than it is to improve over 70-30. So if you're looking at, the two algorithms and saying, which one do you think did a better job? While both people can say I improved over a random guess by 16%, you think the first guy who was starting with 70-30 did a better job. Okay? So it's a thought question, and we'll just go through it. If you have an 80-20 classification and you move it to 90-10, is that better than moving a 50-50 to a 70-30? So in one case, you're improving 10%. In the other case, you're improving 20%. But if you think about it, and if you go from 80-20 and you go to 90-10, you've improved by 10%, which is 50% of what you could do. In the second case, if you improve by 20%, well, you could have improved by 50%, so you've only improved by 40%. So in this, you can make an argument that showing a 20% improvement under these circumstances is not better than the first model, which would improve by 10%. Okay. On to carrot. Now, I think I kind of feel like I promised you to do some carrot, and so let's do some carrot, and I want to do it a little quickly, so stop me if I'm going too fast, because I want to get to the use of carrot and the gradient boosting. Okay. So this is a very well-known example that it ships with that carrot. Okay. So first, I guess I should say, carrot is a package written by a man named Max Kuhn, who currently works for our studio, but he cut his teeth. He was the head of statistical research at Pfizer, I believe, and he wrote this package while he was still at Pfizer, and it's, for many years anyway, is the de facto package for looking and analyzing models. And the main reason is there's a few reasons. One of them is that it provides, a good interface, and it standardizes so many things. I'll show you. So I just loaded Carrot and ML Bench, which is benchmark, which is where the Sonar data set is. Let me unshare my screen. I want to show, rather than showing you the knitted package, I want to show you my code itself, because for some reason when I compiled this, it decided not to show the code. So let me see if I have this. Okay, yeah. So share. I think it's going to be this one. That's the wrong one. Stop share. Yeah. All right. Okay, so you can still see, should I, is this, can you read this print or should I make it bigger?
No, this is good.
That's very fine.
Okay. So all this is doing is I'm loading the data set, sonar data set. I create a random seed, and one of the nice thing it does is it creates a data partition, and I'm guaranteed that the different classes, and this is a classification problem, my training set and my testing set have the same proportion. Okay, so what does Carrot do? It works by doing two things. It allows you to standardize how you're going to, tune your hyperparameters, and it allows you to standardize over what range you want to search from. That's a grid. So for the first example, let's just look at the train control. So I just called it fit control, but the main thing is this function train control. It says I'm going to use repeated cross-validation. I'm going to use fourfold cross-validation, and I'm going to do it twice. Now, in the real world, you would want to do more repeats and probably do a higher number of cross-validation, like 10-fold or 12-fold. It's pretty standard. I chose small numbers because small numbers compute more quickly, and I wanted to make sure I could compile this. I lost the original version I had in a shorter period of time. And if I want to make changes, it's just nice. But if I was really doing something seriously, I'd probably do 10 repeats of 12-fold cross-validation or 10-fold cross-validation. But you just tell it what it is, and it just takes care of all the bookkeeping for you. And then the key function in Carrot is the training function. And one of the things you can do is if your data is of the right sort, you can just give it the same sort of standard formula that you would give to linear modeling. So the class takes value M&R. I want to, compute class compared to all the other variables. And my data is my training set. And my train control is what I've called fit control. And verbose equals false means do not fill my page with electronic garbage of telling me what happens after every step, okay? And I create a model, and then to show you that actually,
So what model was this? Because we did not specify any model here.
yes, I was about to get to that. It turns out that with Carrot, if you don't tell anything, the default is to use random forests.
Okay.
So in fact, this first model is a random forest. And you can see this because I said, show me what GBM fit one is, and you can see it says it's a random forest. And then it just gives me all the information, and it shows me the top things. And you see it gives you accuracy and kappa. So with random forest, all you could do is you could look at the number, how deep it is, how many the M-try, how many variables you allowed. And it said the best thing was to allow 2 variables at every split in the random forest. And an accuracy of 83%, and it improved over random accuracy, but it got rid of about 65% of the errors. We now know what kappa is. Okay? And it just gives you a lot of more information, and here you can see it just is. And another thing you can do with this is plot. Now, see here it shows the boosting iterations and how many, the tree depth and the accuracy as a result. So you can see for all of them, basically, somewhere around 100 trees is what you want with this data set. This is just showing you the summary of GBM fit, which is not very interesting. And the last one it shows is for when you do gradient boosting and you ask for it to plot it, it shows you the variable importance. So it just shows you which variables are more important. Now, this was something, you know, where you would data set like the IBM thing, you'd know what these variables are. And we'll actually do the IBM data set later. Okay, so if you want to do it, you know, so you can create a grid of things. You can tell it, you know, so expand that grid is the name of the function. And then you just tell it the various variables you want to use and, you know, what range you want to do them. So in this case, I said, I usually get tree depth. Remember now we're looking at gradient boosting. So you're using trees. One would be stumps. I looked at 1, 3, 5, and 7. And number of trees from 1,000 to 2,500. And the shrinkage, which is the learning rate, I used 0.1. And the number of min observations in a node, you're doing trays. It says once you get to 25 observations in a node, you stop, regardless, even if you could go further. And then you do the exact same thing. The only difference is you tell it that the tuning grid is what I call gbm.grid. And it'll go through it. And it just gives you get the same sort of information out. It'll just give you the best models. It's a little more confusing now to look at it. But interestingly, notice how the ones that do best have the fewest trees. So consistently, the stumps do the best. Well, essentially, they do the best. You have this little thing where we're here as you increase the number of iterations. You know, I'd be tempted to call these two things pure lucky noise. But of course, if I did more booting of the examples, I would see this. But you can see this shows you that one tree really does the best. Okay, and to show you how to comparison, let's do a support vector machine model too. So in this case, so now I go train and I give it the same thing. I want to compute the class using all the data. I use the same thing of how I'm going to tune my parameters. This I'm going to use the SVM read yield. In other words, you know, the Gaussian, which is one thing, and I just set the tune. There's only one parameter, so I said, you know, do a tune length of 5 and do it. And let's see. So this is again, it gives you the information and it shows you what is best. And here it's computing ROC, you know, as using the measure. And so SQL 32 seemed to work best. And this showed a plot.
What is C here in SVM? Sorry.
What is SVM? The support vector machine.
No, sorry, C. The parameter C.
C is the parameter, the cost. Remember with support vector machines, you give yourself a cost parameter of how much you allow a point to be on the wrong side of the line.
Yeah. Okay.
So when you have large costs, you allow a lot of you allow a lot of points or a few points to be a lot on the wrong side of the line. Right. Okay. And then I, you know, just, you know, to find AUC, you have to, you know, predict is how you find new values. So I use predict. My model is my SVM fit 2 that I did above. And my data is the testing, and type equals probability, so it's compute probabilities. And then you need another package called PROC. And that's when you get the, this is where you got the curve I was showing you earlier. This is the ROC curve for that, for the SVM2 plot. I know what I can do, excuse me. So you can see this it works pretty well, but the data isn't that hard. And finally, if you want to compare models, the key function is called resamples, and you just give it a bunch of models, and it gives you information about all of them. So I had 3 models, GB1, GB2, and SVM. This is GVM fit, GB fit 2, and SVM was just the first. I just picked 3 and you can see you can compare them overall things. So on average, the gradient boosting model was slightly better, but very close. The gradient boosting and sport victim machine worked about well. Now, in this case, they're pretty close, but you can decide which is more important to you, kappa or accuracy. And the SVM fit had a different summary function, so we have to add that in if we want. We have to change the train control for SVM2 to do it, and then I just reran it with there. And there, you can see it. Basically, the only way I can compare things is if they have the same train control. It doesn't know how to compare things if you use different methods to do things. And another thing is, if you want to compute confusion matrices, it's just another function. So I have this model, GBM fit 1. I just call the function confusion matrix on it, and it shows you this. And as a bonus, it adds up and gives you the accuracy. So this is a reasonably decent model. Well, you can see. So this is very fast, but I think this gives you some idea of the power. Once you've taken the hours to get all the, the sort of details of the commas and syntax correct, you can really do this pretty rapidly. And, you can obviously, excuse me, you can create lists of different models with, different sets of training parameters and just feed it all in and just run out and just use the resamples in the end to compare, many, many different models. Okay. I'm going to have to stop sharing for a second to go back and get the okay. Not what I want. I don't have, the last thing I wanted to show you was I did a pretty in-depth study on how you use Caret next GB. And this one is actually, it doesn't have good results, mind you, but it's very interesting. So let me just get this up here. Give me half a second. I'm sorry for this. I thought I had this all set up, but one problem with laptops is that you don't have the screen room to keep everything on there.
While you're searching for that, I'll ask something from Niels. Let's say you have like 500 predictors, right?
Yeah.
And then you don't know that they all predict like your forward return, or let's say Y variable, right? Some of them predict, some of them don't predict, some of them are very highly correlated.
Mm-hmm.
What would be the best way to get down to the few of them which predict the forward? Is like PCA, or is there anything better than PCA? First do PCA.
Depends on what if you're using a tree-based model like the boosting models, they can actually figure out which features